let's get started. Our next speaker today is Jørgen Rennemo, who will be telling us about new derived equivalences via duality of non-abelian gauge linear sigma models.
Right, yes. Yes, thanks for the introduction. Thanks for the opportunity to speak here. So all of this is joint work with Ed Siegel at Imperial College. Right, so you see the title there. So what is this about? Well, okay, so we care about, we start with a variety, and we care about its derived category of coherent sheaves. So I don't know if you do, but I care about its derived category of coherent sheaves. And so the motivating problem we're looking at is that of constructing examples of varieties where you can take two different varieties and relate their derived categories. So either showing they have equivalent derived categories, or where one of them sits inside, one of the categories sits inside the category of the other one. And it turns out, I mean, there are many interesting examples, many ways of constructing these kinds of examples. And so what we're looking at today is basically trying to find new examples of this. This is, I don't know, this is a fun area to work in at the moment because we have this relatively recently developed tool, which you may call LG models and variation of GIT stability. That means something very precise to people working in the area, and I'll try and explain something about what goes into that, which is, I mean, it started out in physics, and then through the work of many physicists and mathematicians, it's now sort of been worked out into a pretty usable and rigorous tool in mathematics. So some of those people are, the references I know best are at the bottom of the slide, and I'm sure there are many I've left out in this story. So what does this apply to? Well, this really helps you understand derived categories of X, which you can describe as complete intersections inside of linear GIT quotients. So you take any affine space, you act on it by a group, and you look at complete intersections inside of that. So for instance, taking your group to be just an algebraic torus, you recover toric complete intersections in this kind of framework. So today we're going to do an example where we apply this strategy. And I mean, the really fun part of this is that in analyzing what comes out of this, we're forced to understand some physical duality of gauge linear sigma models proposed by Kentaro Hori. And yeah, so the upshot is we'll get new examples. So the first thing I want to do is I want to tell you what these examples are geometrically. So they're based on Pfaffian varieties. So Pfaffian varieties are the following thing. You take just the projectivization of the space of n by n antisymmetric matrices. Inside of that, you can look at the locus of matrices having rank at most k, and this gives you the Pfaffian kn. So an example of this is the Pfaffian 2n, which is just a Grassmannian, and sits inside this projective space via its standard Plicker embedding. And we're going to focus on the case where n is odd. You can do this for any n, but the case n odd is slightly simpler. So let's just stick to that for this talk. So this has already been used to give an interesting example, a pretty famous one, which is called the Pfaffian Grassmannian equivalence, which is an example where you can write down two smooth Calabi-Yau threefolds, x and y, and you can show that they have equivalent derived categories. And this sort of, well, one initial interesting feature of this example is that x and y are very geometrically different in that they are not birational. So this is, I mean, I think maybe this was the first example of this kind of phenomenon. So, right, so how do you define these? Well, okay, so there are x and y. Let's just do x first. You start with the Grassmannian 2,7. How can I do this? Yeah. Sitting inside this projective space, and you choose some linear subspace of this projective space of appropriate dimension. Okay, so the dimension here is 14. The point of that is just when you intersect the Grassmannian with this linear space, you end up with an X, and you do an easy calculation, and you show that you get a Calabi-Yau threefold out of this. So the other guy, Y, is going to sit inside the Pfaffian 4-7. And then there's a slightly subtle but very important point is that this Pfaffian 4-7, you want to think of this as living not inside the same projective space as this Grassmannian. This Pfaffian 4-7 lives inside the dual projective space. So you take the dual vector space, you projectivize that, and there you have this, this Pfaffian 4-7 living inside that. So, so defining this linear subspace L, you have a kind of a dual to that, the orthogonal complement. So this L perp is anything which kills L. It lives in the dual vector space. And you take now your Pfaffian 4-7, you intersect it with this PL perp, and that defines for you Y. So there's sort of, the choice of L determines the data, the choice of L determines for you an X and a Y, but the data sort of appears in slightly different ways. And again, you check Y is a Calabi-Yau threefold, and then the hard theorem is that these guys actually have equivalent derived categories. So the point today is so the point, I mean, the main result today is a pretty large generalization of this, showing essentially that this kind of construction works for all Pfaffians, basically. I mean, something similar works for all Pfaffians. So this is not a Calabi-Yau 3 story. This is really a statement about Pfaffians, in a way. Whoops. Okay, so how do you generalize the construction of these X and Y? So what do? Now you look at the Pfaffian Kn. Now K can be anything, N can be anything. Well, let's stick to odd still. You intersect it with a linear subspace of any dimension to define for you this variety XL. Again, you have this, you consider a different Pfaffian, n minus k minus 1, n, living inside a dual projective space. And again, you intersect it with the orthogonal complement. So there are no restrictions here on the dimensions of L and L perp or k or anything. And you'll see if you take k equals 2, n equals 7, that gives you back the example you had on the previous slide. And also, you'll see I'll put little squiggly lines on top of the Pfaffians. That's because, basically, so these Pfaffians are singular varieties, which means that, from our perspective, they're not the right thing to take, and so we have to replace them by some kind of resolution. And actually, we have to take a non-commutative resolution, which, if you don't, I mean, which is basically just, we can define a category which looks like what a category of a resolution would do, but we don't have the actual variety sitting over the Pfaffian. We just have the category. But it's close. I mean, it's you can think of it as being it's close to a variety at a categorical level. Okay, so the theorem, which, I mean, it's been on the slide. You've probably read it already. The theorem is now these X and these Ys are now strongly related, right? So depending on the dimensions of the input parameters, you here Kn and dim-L perp, you can now find fully faithful inclusions of one into the other, or an equivalence between them. So in particular, again, the k equals 2, n equals 7 case recovers this equivalent. That's the middle case here. And this is, I mean, this is a fairly common type of result in this area, and it's like this kind of having inclusions one way or the other or equivalences. And what's happening here is, again, the thing that's usually happening in that the thing which is more negatively curved, general type-like, sits inside the thing which is Fano, and then the equivalence case is the case where they're both Calabi-Yau. So that's the main result of today. So so just a couple of remarks about this. I mean, there's this story about intersecting some variety with a linear subspace, intersecting something else with the orthogonal subspace. That turns out it happens in different contexts. There are quite a few examples of this happening, which and this has been sort of formalized into a theory of homological projective duality by Kuznetsov. And so our result is really, you can formulate it in his theory into the statement that these two Pfaffians, the Kn Pfaffian and the n minus k minus 1 n Pfaffian, are homologically projectively dual. And another thing I should say is I lied a bit when I said we construct new examples of varieties. In general, these are not going to be varieties, because the Pfaffians themselves, or we've taken these Pfaffians with squiggly lines on them, so they're not, so in general, these XL and YL perp will not be varieties. They'll be some kind of singular variety which you can non-commutatively resolve. So you're not going to see new examples of smooth Calabi-Yau 11 folds being derived equivalent here. You're going to see instead like some singular Calabi-Yau 11 fold which you can replace by some smooth category, and these two will be then equivalent. So the fact that you didn't have to do this in the previous Pfaffin-Grassmannian equivalence was sort of an accident of low dimensions. Okay, so I'm going to try and say a few things about the ideas which go into this. So the first thing, so I told you this was a story about complete intersections in GIT quotients. So first off, so the details of this slide are completely unimportant. I just want to show you that it's simple to give a GIT, to give a quotient presentation of the Pfaffian variety. So the idea here is that the Pfaffian parameterizes bivectors of rank at most k inside of this vector space. And instead of parameterizing bivectors of rank at most k, you can take, so a way to give that is to give a map from some symplectic vector space S of dimension k, and then you mod out by the ambiguity, which turns out to be the same thing as modding out by something like the symplectic group of the symplectic vector space. So this gives you, so you have this linear, this affine space here of dimension kn modulo the group GSPS, and that gives you a quotient presentation of the Pfaffian. And if you remember the data and that this Pfaffian comes from this quotient presentation, you can construct this, you can just construct a stack, this quotient stack sitting over it, which if you, this is in some sense a smooth stack, so you might think of it as a stacky resolution of the Pfaffian. So it turns out from a derived categories perspective, it does not at all behave like resolution, so it's not the right thing to take at all. This stack is too stacky. It has infinite stabilizer group, and that means its derived category is a very ill-behaved object in some sense. It's, well, I mean, it's a very convenient object to work with technically, but it does not behave at all like the derived category of a smooth variety would. It's too big. So what we do instead is we define what we call a subcategory of B-branes inside of here. So the analogy is just like, think of this thing as being some infinitely generated guy. Well, and you choose some finite set of the good guys inside here, and you take the thing generated by the finite set of good guys. And that is what we call the subcategory of B-branes. So this is because it seems to match up with what physicists take as, what physicists can compute to be the category of B-branes in some associated physical theories. And then the good thing about this thing, if you, this brain category is now what you get, what defines for you this categorical, this non-commutative resolution. So this is a theorem by Spenko and Vandenberg. And I should say, they're also the ones who came up with the definition of this, although they were not at all, I mean, they were solving a different problem. They just happened to solve ours in the process as well. Anyway, that's sort of a sideline, but it's also like this is a new thing. So I thought it may be of interest to someone in the audience. We'll see. So okay, so I'm just gonna okay, so you should never prove something, right, in a talk. But this, so I think, and I might be wrong, that the proof here is something which has some nice ideas in it, which you can explain even if you don't generally care about derived categories, there's some geometrical maneuvers here which are possible to explain. So it's basically we have 3 steps here. So you start with this complete intersection X inside the Pfaffian. So the first thing you want to do is you want to turn this into an LG model in some way, which I'll tell you. Then you apply variation of GIT stability to turn it into a different one, and then something magic happens where you end up with this this other variety Y that you wanted to get to. So first step, okay, so this is ignore, like if you haven't seen this, you should probably ignore everything here except for the idea. So the idea here is to write XL as a critical locus, right? So XL is a complete intersection. It's given to you as a complete intersection, which means there's a canonical way to express it as a critical locus. Okay, so XL sits inside this quotient stack. So you have functions on this linear guy, Hom SV, functions Fi. To write XL as a critical locus, you just add on extra directions L perp with coordinates Pi. You write down some potential where you just pair up the Fi's and the Pi's. And since this is linear in the Pi's, that means that the critical locus of this potential is actually XL in some nice way. I mean, there's lots of technical. The nicest way possible you can write XL as a critical locus. This potential behaves nice both locally and globally. And so the categorical incarnation of that fact is that if you now look at what the derived category of this pair E with potential should be, which is the category of matrix factorizations, then that reduces just to the actual critical locus itself. So you just get this derived category of X, this critical locus, is the category of matrix factorizations. And again, there's this technicality that this thing is a horrible stack, so you have to take the nice subcategory of B-branes. But this has transformed your X into a category of matrix factorizations. And what does that buy you? So that buys you, now you access variation of GIT. So remember, XL is not a GIT quotient itself, it just sits inside one, right? Whereas this space E, by construction, is a GIT quotient. So basically, you have this E, which is a quotient. So you modify it slightly to something which is a birational quotient. So just you change it into a different one. And now, because of some important work by Halpin Leisner and Pavel Katsarkov, we have a good handle of how this changes the derived category. And in this particular setting, the answer is it doesn't change it by very much. I mean, well, we know how it changes it. And you get what you expect, equivalences or fully faithful inclusions one way or the other. So, okay, so now you've come a long way. I haven't emphasized any of the details enough here for you to be able to see this, but I now claim that this guy naturally lives over PL perp. So X and Y are they're very far from each other geometrically, right? They don't live in the same space at all. There's no obvious geometric connection between them. Now you've changed X into something which lives over PL perp. YL perp, by definition, it's an intersection with PL perp, so it lives sort of inside PL perp. So you're almost there in some sense. You're working over the same space. And you can hope to now analyze this fiber-wise or locally over PL perp and show that they're equivalent. And I won't tell you why, but we basically can't. This category, the fibers of this category are too complicated for us to understand them in general. So we're basically at this point where, well, we used to be essentially stuck. But, so this is where physics incarnated by Hori comes in and saves the day for us. So we had this thing S, which we used to define this GIT problem, which was a symplectic vector space of dimension k, we now define a new one of dimension n minus k minus 1. And then we consider Hori considers two gauge linear sigma models. And this is where I do the usual thing and admit I don't really know what a gauge linear sigma model is. But I know enough to say that the relevant data for me is just an affine space with a group action and a potential on it. So this first one, this guy is just the thing we had. This is the thing that was on all the previous slides, the thing that we used. This was the GIT problem that we considered. That gave us these E's and the E primes with the natural potential. And you can see I've just sort of changed an L perp into L, changed the ordering of things around a bit here. To do so, you can sort of believe that there's the analogous theory defined, which looks almost the same. And then the claim is that these are, in some sense, equivalent. So I'm not sure if equivalence is the right thing to say here. I was recently informed that a potentially useful thing to say is that this is a 2D version of Seiberg duality. So yes, so that's said. Anyway, so the reason I feel comfortable saying this is because we can actually prove one incarnation of this this equivalence. We can prove that this holds at the level of the B-brain categories. Okay, so it's not you're not meant to understand what this statement says, but it's just this. You can take the B-brain category of one and turn it into the B-brain category of the other one. So this basically finishes the proof for us. So what have we done? We took our thing, our X, we turned it into some factorization category. VJT turned it into a different one, and this was this thing. By definition, it's this thing, which we couldn't analyze. It was too hard. Hori's duality now allows us to just change this into a different thing. You change the SS out for Qs, you trade the L perp for an L in a certain way. And the point of this is that now this thing turns into something which is very easy to analyze. So you had this critical locus trick of writing, so this thing you can write it as critical locus and turn it into an algae model. Now you just run this in reverse and you take the critical locus of this thing and it becomes this thing. So in this setting, the critical locus has this niceness property which allows us to reduce it to just the category dy of dy L perp. So this is yeah. So this gets us where we want to be. Okay, so here's a picture of the same thing. We have this. We have one GLSM where you start out with XL. This is some GIT phase of one GLSM. VJT allows us to get to here, and this is the bit that we sort of already knew how to do. And then Hori's new duality is this magic thing which allows us to teleport into a different GLSM where we land in the easy point in the dual GLSM and allows us to analyze this geometrically. So the final remarks is that this is a duality for SP. There's an analogous one for orthogonal groups, which geometrically reduces to some statement about symmetry. I mean, loci of symmetric matrices of given rank. So what we had before was Pfaffians, which was anti-symmetric matrices of given rank. So this is work in progress, working out the orthogonal case, which should be fairly similar. And finally, you can sort of, I mean, so what you can mash these up, combine these in different ways, add on C-star factors. You can write down some more complicated things, and you get more examples. So this is not just a statement about linear intersections with Pfaffians. There's more flexibility to generate more examples and analyze them in further detail. So yeah, thanks.
Questions?
So I wanted to ask you a naive question. In the original story of the Grassmannian 2-7, Fabian 7, points in the Fabian were parameterizing curves in the Grassmannian 3.
Right, yes.
So for these higher dimensions, do you have can you, first of all, your composite map going from derived category of X to derived category of Y?
Yeah.
Did you check if it is some Fourier-Mackay transform?
Okay, so I mean, it is a Fourier-Mackay kernel, but we haven't even thought about trying to analyze what it does, whether it does anything sensible geometrically. So yeah, I mean that's an interesting question, but we haven't begun thinking about that yet.
Okay.
Other questions? If not, let's thank the speaker again.